a computational approach to packet classification. My name is Alon Rashelbach, and this is a joint work with Ori Rotenstreich and Mark Zilberstein from the Technion, Israel. Network functions such as access control, quality of service, packet forwarding, firewalls, and many more classify packets in everyday life. Packet classifiers look on the header of each packet and decide what to do with it according to a set of rules, each with several fields such as source and destination IP addresses, source and destination ports, IP protocol, and more. For instance, OpenFlow 1.4 supports matching up to 41 distinct header fields. Each field can be exact match or have wildcards such as longest prefix or numerical ranges. Rules may overlap, so the classifier selects the rule with the highest priority. Classification can be performed in both hardware and software. Hardware classifiers are possible thanks to a dedicated component named Ternary Content Addressable Memory, or TCAM, which is a power-hungry ASIC that performs classification in a single cycle. We focus on the alternative, software classifiers that use commodity hardware instead of a dedicated middle box. Classification algorithms usually take part in virtual switches. So let's look on our virtual switch. We gave it some set of rules and now it's busy classifying packets. Everything is okay as long as there is only a small amount of rules. When we try to add more rules, we get a drop in throughput. And it doesn't matter which classification algorithm we're using, all experience the same phenomenon. Large rule sets spill out of CPU core cache, causing expensive L3 cache accesses. Just to understand the impact, L3 cache access time is 10 times slower than that of L1 cache. This is devastating for packet classification. You may ask yourselves, how bad is it? Well, let's look on a real example. Tuple merge is a state-of-the-art algorithm that uses hash tables for classification. It requires the same amount of computations regardless of the number of rules it holds. The only thing that changes is its memory footprint, which you can see on the left. Note that large classifiers, meaning 100,000 rules and more, spill out of L2 cache. On the right, you see the throughput of the same classifiers. By the way, these experiments were performed using the standard ClassBench benchmark for packet classification. Notice the performance drop of the largest classifier, which is the rightmost point in the right graph. It is twice as slower as the smallest classifier. The reason is the slow access time of the L3 cache. We make the following observations on packet classification. The rule space is sparse, meaning rules cover only a tiny fraction out of all possibilities in all fields. L3 cache and DRAM accesses are the major bottleneck, as they're not integrated in the CPU core, and hardware trends toward commodity accelerators, such as wide vector processing engines that make computations much faster. These all make us wonder whether packet classification may benefit from trading memory accesses for computations. Classification in the presence of wildcards is similar to range value lookups, in which we search for the range that contains an input. Here, for example, the input 175 is contained within the highlighted range of 150 to 200, which corresponds to the value C. By storing the ranges in a contiguous table, we can represent them and their offsets in table as a function, then use a model to approximate that function. We do that using a data structure called Range Query Recursive Model Index, or RQRMI for short. RQRMI models support fast and efficient range value lookups. They consist of multiple neural networks in a staged fashion. Only a single network is evaluated per stage. All networks solve the same regression problem. Given an input X, they try to approximate the matching range that contains X. The outputs of internal stages are used to choose a network in the following stage that has a better chance to be successful. Let's see an example of how RQRMI works. We have a set of range value pairs and say we trained an RQRMI model for approximating them. Now, we wish to find the corresponding value for the input 801. We feed it to the model and get an approximation for the memory offset. F hat x equals 103. Say we know that approximation error is bounded by epsilon equals 1. So we go to the table and perform a secondary search over the ranges around the model approximation. More details about the RQRMI training technique and correctness proofs are available in the paper. We also show how to handle multi-dimensional rules with multiple fields. We term our solution to packet classification as NuevoMatch. It trades memory accesses for computations using RQRMI models. They store between 70 to 100% of the rules, while the rest is kept as a remainder and classified using any existing technique. We elaborate more on how we choose which rules get into the models and which get into the remainder in the paper. The classification is performed using real-time neural network inference. The remainder is evaluated only when we can't find the matching rule using the RQRMI models. In the end, NuevoMatch guarantees that both RQRMI models and the remainder will always fit in the L2 core cache. Let's see it in action. Here are cut split, neurocuts, and tuple merge, all state-of-the-art techniques for packet classification. We measure the memory footprint using the standard ClassBench benchmark for packet classification. Almost all methods spill out of L2 cache for large classifiers. Compared to them, NuevoMatch hardly reaches the bounds of L2 cache. We ran NuevoMatch 3 times. In each time we use a different method for the remainder. The red bar represents RQRMI models, the orange represents the remainder. By combining small and shallow neural networks with wide vector instructions, we can evaluate an RQRMI model within 40 to 50 nanoseconds. Adding the secondary search and the remainder, the end-to-end classification latency varies between 100 to 300 nanoseconds. NuevoMatch supports updates. We can easily remove rules from RQRMI models and insert new ones into the remainder. After passing a threshold in the number of new rules, we retrain the models. Our experiments show that training with TensorFlow takes about 10 to 40 minutes on a CPU. However, in our ongoing work, we achieve training time of between 1 to 20 seconds on a CPU using native implementation. More information on NuevoMatch, such as its scalability to the number of classification fields, multi-core evaluation, and an early termination optimization are described in the paper. Let's talk about evaluation. We experiment end-to-end performance and detailed analysis of various aspects. In this video, we will focus only on the end-to-end performance evaluation using traffic with uniform temporal locality. Real-world classifiers such as OpenVSwitch employ caches to catch the temporal locality of the traffic and invoke the packet classifier only upon cache misses. We simulate this behavior by testing NuevoMatch using traces with uniform temporal locality. We use ClassBench to generate 12 distinct rule sets with 500,000 rules and compare against 3 state-of-the-art techniques. In all rule sets, NuevoMatch exceeds all other methods. The GM on the right stands for geometrical mean. Note that some bars are missing. These are neurocuts classifiers that did not converge. To conclude, NuevoMatch introduces a new point in the design space of packet classification algorithms and opens up new ways to scale it on commodity processors. This is possible thanks to RQRMI models that support fast lookup of range value pairs. It is important to understand that NuevoMatch is not operational in a real system just yet. This is the goal of our ongoing work. More details are available in the longer version of this presentation and in the paper. Thank you.
All right. Thanks, Alan, for an awesome talk. So while we are waiting for questions over the Q&A tool as well as Slack, let me ask some of the questions I have. So you have this machine learning based approach system, right? And let me play the devil's advocate here that network operators have hard time trusting machine learning based solutions or deploying machine learning based solutions because they don't trust that these will perform well in the production settings, right? So what steps will you take to establish that trust, or maybe there are some approaches that you have already proposed in the paper to establish that trust to kind of bridge the gap and have this deployed in production settings?
Yeah, this is a good question. It is important to understand that the machine learning part in NuevoMatch is is not a bottleneck, and it's not the cause of any problems because it's part of the CPU. We run the machine learning part using wide vector processing engines, which are available in almost any modern CPU. So network operators don't need anything else.
Okay, cool. All right, so I have a question from Hyojun Kim, and his question is the neural network model structure fixed? That is the number of layers and nodes that you're using, or does it change based on the traffic characteristics?
This is also a good question. In a matter of fact, the structure is fixed, and creating a dynamic structure is the goal of our ongoing work. Okay.
So I think I have one more question, which is my question, that this RQRMI tool that you're using in this paper is exciting. So I can see there are a lot of other networking problems where this can be used. So what is your view on what other networking problems where this tool can be useful?
Let me repeat the question. You're asking whether RQRMI can be used on different applications, in different applications?
Yeah, different networking related applications.
This is a very good question. We're currently thinking about it. In network applications, we can use RQRMI. We're thinking about implementing it using combined with sketches to collect network information. We don't have any specific goal just yet. We're in the process of thinking. Yeah.
Okay. One more question, and this is from Hun Namkung, and his question is, how long does insertion or training takes compared to adding rules into the table?
Yeah, so using TensorFlow training takes a long time, but in our ongoing work, we achieve super fast training, even sub-second training for the whole model. So compared to a rule insertion, you can say it's maybe 3 orders of magnitude longer, but we can use a remainder that supports fast insertions while we train. So it's kind of a buffering while we're training, and then we do a switch on the trained model.
Okay. So yeah, I think I guess somebody else is asking, but yeah, okay, there is a question. So I think that the talk said, and this is a question from Ben Paf, and I think that the talk said that the rules can be added to the remainder for updates. Does this mean that the added rules cannot override any previously existing rules, or is the remainder always searched?
Can you ask the question again?
Okay. So the talk said that the rules can be added to the remainder for updates, right?
Yes.
So does this mean that the added rules cannot override any previously existing rules?
They can override. There isn't a problem. When you insert new rule that overrides any previously defined rule, you just invalidate the previous rules, and you can do it you don't need to retrain the model in order to do so.
Okay, all right. So in interest of time, let's move this discussion to Slack. I think there are more questions over Slack, and you'll be, interested in answering those as well.
Great. Thanks, Alon. I think it's a very cool and very great talk. So I think there are several questions online. So the first question is, in one of your slides, you showed the difference of the training time between the TensorFlow and the native version, and why is that? Why is the gap?
Yeah, that's a good question. I think it's because TensorFlow is not optimized to small neural networks. The native implementation is just C code. So when we run using native C, native implementation, it's just faster. I can't explain it, really.
Okay. The second question is, are there any cases where there are misclassification by the model?
Oh, this is a very good question. We prove the correctness of our method So the classifier will always succeed. No misclassifications.
Well, here I have a following question. So you mentioned about you're using machine learning model, right? So when you mention about machine learning, the first reaction of me is that it's kind of probabilistic. You always have some probability that the model is not working. So why are you saying that it kind of is theoretically sound?
Yeah. So the model is probabilistic, but we have guarantees on its error. So recall that the process is composed of a model neural network inference and then a secondary search. And the secondary search eliminates all the error caused by the model.
Thank you. So actually, myself have a question. So it seems that your job is kind of in the background, that you're doing this in software switch, right? So what do you want to do is to get more cache, so CPU cache. So, but there's one direction in industry that they move the kind of virtual switch to the smart NICs, either the FPGA or the T4 NICs. So is there any comments, or if that happened, so would there be any kind of, how do you compare these two kind of directions?
Yes. In our ongoing work, we wish to implement our method in SmartNIC. So as long as the processors on the SmartNIC support wide vector instructions, they can run NuevoMatch.
Okay.